this is the sorry, the recording message came to me here. So this is the agenda for the next hour. We're starting with an introduction to ACAN and existing building group, and then we go to the main presentations. First, Simon Jones from Air Quality Matters, and then we'll start from Etude, and then we'll finish with a Q&A session. So let's start with an introduction to ACAN. We are in a climate emergency. We cannot be passive about it, and we need to take action. Our manifesto and overarching aims are decarbonize now, looking for regeneration and cultural transformation, and challenging the current way of thinking for an holistic change. We do organize as ACAN a large amount of events, both in person and online, and we are organized in 9 thematic groups. And these presentations will be organized by the existing building groups. So existing building, we have been doing in the past a number of publications, webinars that you can all find in the YouTube channel. And our current campaigns are a campaign against demolition with a demolition map that we launched last year. Then we are working on a community retrofit map that is for connecting community retrofit groups together. That is going to be launched soon. We are also working on a retrofit with natural material workshop, but that is still work in progress, and we'll let you know more in the future. And then the technical webinar series, that is the one we are doing now. We started in October with an episode about vacuum glazed windows. Then we did natural material insulations for retrofit. And today we're talking about ventilation and air quality. And in the summer, we're going to have one about heat pumps. Don't forget to support us and become a member of ACAN. And we can now start with the main presentation. So Simon, up to you if you want to.
Thanks, Federica. I hope you can hear me well.
I'll stop sharing.
And I'll try sharing there. So hopefully that's working for people.
Yes.
You can see my screen?
Mm-hmm.
Perfect. Good morning or afternoon, everybody. Nice to meet you all. I'm going to give a little bit of an introduction presentation. Will's going to follow and take a little bit of a deeper dive, particularly into heat recovery and the practicalities of ventilation in buildings. But what I thought I'd do is start out with a little bit of an overview on air quality and why it matters, and some kind of basic principles around ventilation, because often what we find, particularly in the built environment, is that often some of the mistakes we see and bad outcomes with ventilation is often down to very fundamental misunderstandings of what it's for and what we should be asking for. For those that don't know me, my name is Simon Jones. I wear a number of hats in life, one of which is I'm a host of a podcast called Air Quality Matters, where I speak to people all over the world about this subject. I'm a secretary for the International Energy Agency's research group on energy in buildings and communities, where we manage anything up to 600 groups of researchers at any one time looking at this sector. And thirdly, I'm a typical consultant working in this space, advising organisations on ventilation and air quality, particularly around communicating on the subject. Why do we care about buildings when it comes to indoor air quality? Well, if we're lucky enough to live to 80 years of age, we're going to spend close to 70 years of our life indoors. We are the indoor generation. 55 years of that life will be at home in our own buildings. So whether we like it or not, our homes have a profound impact on our long-term health and well-being. In fact, we'll spend 25 years of our life asleep in one room. We're often, and we hope, asleep and not able to actually interact with that space. So our homes have a profound impact long-term on us. In fact, so much so that even the majority of our exposure to outdoor air will occur indoors, just because of the pure maths of the amount of time we spend indoors. Why do I have two pictures of water on my screen? Well, the interesting thing about our environment is in a lot of cases, we have choices. If I don't like the taste of water where I am, I can wait until I get home before having a drink. We don't get that choice with air quality often. I don't know if any of you have tried waiting until you get home before you take a breath, but it doesn't work out very well for you very often. And for this reason, air pollution is the single largest environmental risk we face. It's something that we consume every second of every day of our lives. And even within Europe, in 2019, which were the latest figures, close to 600,000 premature deaths can be associated with air pollution, 154,000 of those indoors. So the numbers are absolutely staggering. And if we take something as specific as asthma, a condition we know is significantly exacerbated by indoor conditions, 5.4 million people in the UK currently live with this condition. In Ireland, where I live, every 4.5 minutes, somebody is admitted to hospital with an asthmatic condition. And we know buildings have profound impacts on our respiratory health and our long-term health. In Europe, it's estimated that nearly 80 million people live in homes with some form of damp condensation and mold. Um, it can be as high as 25 to 50% of the building stock can have some evidence of damp and mold within it. And we know ventilation is a critical pillar in controlling many of these pollutants, yet every single time we look at this sector, we find profound problems in meeting even the minimum standards. And we have to remember that minimum standards are often the worst possible air quality allowed by law. They're hardly a reach target. Um, a simple example of this is one of the most recent studies in the UK, which surveyed homes across the spectrum, new, old, different tenures, found 71% of those homes did not have the ventilation provisions that met the current building standards. That's not the performance of the ventilations, that was actually missing component parts that would enable that system to be compliant with modern regulations. And this figure is repeated globally. Across Europe, one of the largest studies that was done found between 20 and 55% of homes actually had measured flow rates that were below regulations. And 55 to 75% of those homes were operated in a way that meant they had lower rates, even if those systems were capable of doing so. And even in countries that have a fairly advanced view of ventilation, like Scandinavian countries, 50% of the balanced systems were either out of balance or malfunctioning in some way. So we have a huge gap. We have a huge problem with the impact of air quality, and we have a huge problem with the performance of the systems that we're currently putting in there. Why is this? Well, we don't think about the impacts of indoor air quality on our health. We've been talking about ventilation and indoor air quality here now for 10 minutes. And not once has anybody on this call taken a breath and actually physically thought about the quality of the air that we're breathing. We're physically hardwired not to think about air quality. And up until recently, it's been very expensive to see the air that we breathe. But mostly, in my opinion, it's because we assume that because a standard exists, that somehow the supply chain will deliver. And we deliver ventilation in the majority of cases based on specification of product, not performance. So what do I mean by that? I mean, when we try and work out whether there's adequate ventilation in a property, we often consider that because a fan exists on a wall and it makes a noise when the light comes on, that somehow we magically have ventilation. And that clearly, from the research that I saw in the previous slides, is not the case. So what do we mean by air quality? If I was to give you all a jar right now and you were to close a lid and send it off to a lab, what would we find inside our buildings? Well, usefully, there's been some good work on this recently, and we found in our type of buildings, there's typically around 180 common pollutants that we know cause harm to human beings. Here's a nice visual representation of that in a tree plot that looks at the most common. And what you see there is a mix of volatile organic compounds, particulate matter, and gases from combustion, the sorts of things we expect to see, including things like limonene and pinene. Limonene there, 3%, is quite a common pollutant found in home. And that's basically anything that smells zesty, fresh, or lemony in your home, like floor cleaners or wipes or anything like that, usually contains limonene. Interestingly, limonene, although it's relatively harmless, when it comes into contact with things like ozone, turns into formaldehyde and particulate matter, pollutants that certainly are not harmless. So when we actually look at the harm these pollutants cause, what's really interesting is that we start to see some common pollutants stand out as the most harmful pollutants we're exposed to in the home. By far and away, by an order of magnitude, fine particulate matter represents nearly 75% of all the harm we're exposed to in a home, followed closely by formaldehyde, so off-gassing from building materials, nitrogen dioxide, which is products of combustion like gas cookers and traffic pollution, radon, and ozone. And the other 180 of them are all represent those small boxes in the corner bottom right of your diagram there. Together, these pollutants represent about 2,200 years lost of life per 100,000 of the population. This is a metric we use in public health called DALYs, and we use this as a way of understanding how risky a certain risk is to the general population. To give you some equivalence, smoking represents about 2,600 years lost to life per 100,000 of the population, alcoholism around 1,000, road traffic deaths around 1,200. So the quality of the air that we're all exposed to in our homes right now is equivalent to the population smoking and is twice as harmful as road traffic deaths and alcoholism. Yet, when was the last time you saw a public health campaign talking about the quality of the air that you breathe indoors? And why is this stuff so harmful? Particulate matter, which, as I mentioned, represents nearly 75% of all the harm, is effectively the Trojan horse of air quality. These fine particles that get deep into our lungs are so small, at 2.5 microns in width, that they cross the blood barrier into our system, which means once they're there, they're circulated to every organ of the body. And these particles are not inert pieces of carbon. They carry heavy metal from industries and combustion. They carry VOCs and flame retardants from the materials that they settle in our home. They're vaporized when we cook on our cooker. And produce polyaromatic hydrocarbons and other pollutants when we cook normal food. All of these pollutants are finding their way into our body, and we now know they're closely associated with almost every major disease that we have. One of the things people often comment on is on your pollution chart there, Simon, I didn't see mold. Interestingly, the next smallest blue dot, it represents roughly 1/4 of 1% of the harm we're exposed to in the home, is mold, or actually bioaerosols, which includes viruses and bacteria as well. And people are often surprised at that. And the reason is that this is a population level calculation for starters. So not every home has damp and mold in it, whereas every home is exposed to particulate matter. But actually, we find particulate matter very harmful. But the interesting thing about mold is it's associated with condensation and damp. And the interesting thing about that is it's one of the few pollutants that causes harm to the building fabric itself as well. So we, of course, pay quite a lot of attention to it because it's ugly, it damages buildings as well as health. And nowadays we start to think about moisture in the sense of moisture risk. And this idea of balance between systems, fabric, activity, and the context that the building sits in. And all of these things come together, and every building will have a slightly different balance point. All of these things come together to create a healthy building. The interesting thing about all of these, the main pollutants that we were talking about, moisture risk in building, is that we already have the levers that we need in order to protect ourselves from a lot of these pollutants. And one of the biggest levers we have is ventilation. Yet time and time again, we see serious misunderstandings of exactly what we're talking about, particularly at a consumer level. How many times have you all been into buildings where you go, oh, I notice you've got heat recovery ventilation? And the response is, do I? So, there's a profound gap between the knowledge of people that are using systems and what they actually have. So here's a quick ventilation basic run through because I don't have too much time. But principally, there are two forms of ventilation in a home. Ventilation that's there for the purpose of ventilation and ventilation that's there through gaps and infiltration and leaks in the building. But what we're principally talking about here today is ventilation that's there on purpose. And I want to talk about three or four typical systems that we're coming across. Most common of which is natural ventilation and intermittent fans. And what most people see as natural ventilation is holes in a building where cold air comes in. But what we don't realize actually is that there's a process of fluid dynamics going on where you get different pressures on different side of the building. And what's happening is that gases are trying to balance the whole time. And that's why you get cross ventilation through a building, not because air is blowing in a hole, but because pressures are trying to equalize through a building. And what we often find is because people's lived experience of natural ventilation is this living room is drafty because that's where the air comes in. People's lived experience on the other side of the property where the warm air is going out is that I don't have a problem there because you can't feel cold air coming in, warm air is going out. So what happens is people start to shut vents off on the cold side of the building, but what that does is cut off at the knees the process of that cross ventilation. So when we go into properties and we see a couple of vents closed, and if any of you live in a house with natural ventilation, I'm sure there's one or two vents that you have shut because they're the drafty ones. What you're actually doing is stopping the entire process of cross ventilation. One of the other challenges we have with natural ventilation is that we don't control the direction of airflow. So any pollutants that are generated in this circumstance here in the bathroom, where do we think they go? Well, they go into the rest of the property. They're blown around. And that's why it's so important when we have natural ventilation, we have functioning intermittent fans. Unfortunately, these fans are often the cheapest possible pieces of equipment you can buy on the market because there's no inherent value in them or perceived value in them, which means they don't do a good enough job of removing those pollutants. And that's why we find considerable amounts of condensation, damp, and mold with this type of system. Increasingly these days, we're finding more. So I was just checking my time because I have a terrible habit of overrunning. Interestingly, now we're now moving into continuous mechanical systems, and one of the most common types that we're seeing now in the market is continuous extract. And what those systems are effectively doing is again working with pressures in buildings. They create a negative pressure in this case, rather than a difference between one side of the building and another. By creating a negative pressure in the bathroom because they're sucking air out of it, it creates a negative pressure from the room next door and pulls air in and then in from outside. So we get this chain reaction. The advantage of that is that we're now in control of the direction of airflow. We're always pulling out of moisture and polluting generating rooms and always bringing air in through habitable spaces. One of the most common reasons we see failure of this type of system in the marketplace, besides poor ventilation flow rates, are short circuits. So where you have an extract in a room that also has an inlet, so you might have a Velux with a hatch latch on it, or you might have a trickle vent in a bathroom, we create short circuits, which again cuts off at the knees this pressure process and creates a process of air exchange in one room, but doesn't draw in room air from the rest of the property. Increasingly these days, we're seeing decentralized versions of this technology. So they work in exactly the same way. They look like bathroom fans, but they're now always on. And the important thing to remember with these systems is that we need them to be robust enough to move the amount of air that we need. And particularly in retrofit, that can be quite challenging to do because we often don't have as many wet rooms in older and existing buildings as we do in the modern ones. And I won't spend too much time here, but we'll talk about it in more detail. But increasingly now we're starting to move towards heat recovery ventilation. And this is where we have air supplied to every habitable space and air extracted from every moisture and pollutant generating space mechanically all of the time. And in the process, recovering the heat as it does so. The challenge with existing buildings, as you'd imagine, is that there's a little bit more infrastructure with this type of system. But what we find is even in the less well designed systems, they may not be performing from an energy perspective, But if you are mechanically supplying air 24 hours a day into habitable spaces and extracting it 24 hours a day from wet spaces, from an air quality outcome perspective, you often get better results than you might do with some of the other systems. The challenge, though, is when those filters aren't changed or when they're not set up correctly, we don't have any background source of ventilation to compensate in their absence. I want to touch very briefly on a couple of other approaches because it would be remiss of me not to talk about them when we're talking about systems. Demand control ventilation is this idea that you might often see it with extract type systems, but it's a control strategy rather than a system in itself. And it's this idea that you manage the amount of air that's moved in a building based on the air quality that it measures. The advantages of that is if they don't need much ventilation, you can save energy. And if the building has particular demands, it can meet those demands pretty effectively. How am I doing for time? I'm nearly at the end here, am I, Frederica?
Yes, nearly there, I think.
Okay, I'll try and wind up.
About 3 minutes, yes.
Yeah, I'll just skip over PIV and single room heat recovery. But what I would say about those systems is that we do need to be a little bit careful that there are alternative approaches that are available in the market, but it's very important that you engage with people that really know what they're talking about with these systems because often they're missold as a silver bullet for something that they're not. And there's a reason why, whether those system producers like them or not, that they're not in ADF and some of the regulations in the same way as some of the systems I've just been talking about. Often because they're performing a bit part of a whole ventilation solution, or they have a history of being used in a particular way. A PIV comes to mind where they've been an add-on to an existing system to help rather than a system in of themselves. So it's been very difficult to get those systems recognized for good reason. I just want to finish very quickly on performance. None of this matters if ventilation systems don't perform. And it's really important for us, if we remember anything about these presentations, that it's the performance of these systems that matters. And as complex as some of these systems are, they all fundamentally perform the same three acts to provide good outcomes for a building: background ventilation, local exhaust ventilation, and the ability to purge a building. These are the three pillars that provide us with good air quality. We are now looking, with the deterioration of outdoor air, at perhaps a fourth pillar, which is air cleaning, but that's for another presentation. So what do I mean by background ventilation? Background ventilation is this idea that every building needs a certain amount of air renewal 24 hours a day to limit the build-up of pollutants over time. Um, it's very important that this happens effectively. The challenge we have with natural ventilation is it's very difficult for us to predict what that background ventilation is going to be. And here's just three examples of a whole range of different houses and different orientations. It's incredibly difficult to predict what one of those particular houses is going to do on any particular day. Whereas mechanical systems, we start to get to make a choice ourselves. We can say we want a system to do X, and if that isn't enough, we can turn it up a bit, and if it's too much, we can turn it down a bit. And the calculations for these standards are not hard. The problem is that we don't specify based on outcomes, we specify based on product. And we need to get better at saying, I need this system to do X rather than saying equal or approved to a Ventaxia unit or whatever your favorite flavor of ventilation unit is. And because the reality is that the system is built to fail. When you have a system built on minimum standards, which is the worst possible ventilation allowed by law, any failure in that supply chain to fulfill its part means automatically you don't meet that minimum standard. It is the flaw, not the goal. And in every case, we absolutely have to start thinking about building in capacity and tolerance into these systems that enable us to build a higher ceiling for better outcomes. And none of this matters if we don't measure. Measuring is not, does it hold a bit of tissue paper up when I put it up to the ceiling? And it is not, does it make a noise when the fan comes on? Measuring is using equipment that's purpose built to measure the precise airflow rates of these systems that we install. If we're not measuring, we can't manage it. That's the end of my presentation. Thanks very much.
Thank you, Simon.
Hand over to me, presumably. Great. Thank you very much. Cool. Hello, everybody. Yeah, thank you, Simon. That was really interesting. I learned some things there about formaldehyde and lemons flavored sprays. That was really good. So yeah, and I wondered whether your fourth pillar was going to be energy. So maybe there's a fifth pillar. So I'll have to introduce the sort of consideration of that as well. I'm Will South. I'm an engineer and I work at Etude. I am a designer and an engineer background, and I work as a consultant, but I have done a little bit of MVHR or ventilation system install. So this is me being practical, and I wrote a video about it, but I'm not an installer. So I've installed four systems, and that's not enough to make a living on. So this is just those experiences. I'm going to talk around the hardest or the let's say from my point of view, the best system, the most desirable system, which is the whole house mechanical ventilation with heat recovery. So a full house system, mainly because that is the hardest. And if you can do that or think about that, and then rein it back to maybe a different system that works for your project where it's needed, then that's a sort of a good starting point. Um, and a lot of this, whether you're doing continuous decentralized extract or centralized continuous extract or mechanical ventilation with heat recovery, all sounds very complicated, but essentially is getting some ducts with some air in them to various parts of a property. So that's the sort of main challenge I'm going to try and address here, the practical part. I mentioned energy. I think it's really important to understand that the cold air that you're bringing into the property through the winter months and actually really, through to April, probably starting from October, whenever the outside temperature is colder than you want it inside, you have to heat in some way. And that will either be through the internal heat gains, cooking, that sort of thing, or will be through your heating system. Um, and when we do the numbers on that, we find that the energy required to heat the cold air is a lot more than the energy required for the electricity for running fans. So the sort of thought of the natural ventilation, oh, it's like passive, it's really eco, actually is wrong because we've then got to heat the stuff. So this is just looking at this graph looks at the total heating energy that you need with two systems, one that's got heat recovery and good air tightness, and one that doesn't have heat recovery and achieves a similar level of ventilation air. And you can see that the big orange bar goes up quite a lot. It could go up more than that. I've been quite conservative there. I've assumed that MUV's got demand control and things like that. So the bit of energy which is blue, and this is all electricity, um, is the fan power, and it's fairly negligible. It's smaller for the extract fans because there's only one fan extracting, whereas with the supply, there's a supply fan and an extract fan. So yeah, just good to know that that's the main impact of ventilation in terms of energy is having to heat that air and having to cool that air. If you were in a hot climate, it would be the same, but you'd be having to cool the air. So it's similar. Good. So one thing right up front, I just wanted to bust a myth. So with retrofit properties, it's really difficult to achieve good air tightness. And although we want to improve air tightness and reduce the unwanted ventilation, if you like, the infiltration, as a sort of quite cost-effective way of reducing our energy bills and carbon emissions, um, the sort of myth prevailed that you wouldn't get any benefit from heat recovery unless you met a certain low number. And that's quite difficult to do in old properties to the extent that maybe you would never achieve that. I worked really, really hard on my house, pretty much taken a lot of it apart, and I got to two tightness, air permeability of two. Passive house is less than one. So yeah, I'm double passive house. Um, the myth was that you needed a certain level of passive house to get any carbon savings. And this is basically from SAP9 calculations, which had this crossover point at about 3 meters cubed per meter squared per hour. If you unpick what that calculation is doing and sort of rehash it, that's just we're going to provide the same amount of ventilation air, and there's two options. We do it with heat recovery or we don't do it with heat recovery. Then the picture's very different. And actually we find that MVHR or some heat recovery is always beneficial. So that's just saying, even if you can't do the air tightness, it's still worth doing balanced supply and extract ventilation. Some of that is around the pressure diagrams that Simon showed there, and sort of guaranteeing that some bedroom, which is quite sheltered and doesn't have any holes in it, actually gets ventilated. So yeah, it's just that pushed it in. Good. So we want to do this. That's the aspiration, and maybe that's why you're here. Um, and let's start at that sort of, can we do the best case? So it's really difficult, undoubtedly. And here's some sort of things that you might cross your mind. Oh, it's difficult to run the ducts. Oh, I've got no space for a big fan unit. Oh, there's going to be some unsightly boxing in. There's some knock-on works I've just decorated, and now I'm going to have to drill big holes in everything. I'm going to lose some floor area, maybe because of that big fan area or boxing in. Maybe there's some structure which you just can't get through, and actually it's going to cause issues. So those all exist. They're all real things. They existed on the projects that I did. Um, but I think my sort of rule of thumb is there is always a way. There's going to be some compromises, but for a group of designers, the challenge is design. You need to do the design and try and build it in, and it be part of one of the things that you want to achieve. So that's sort of the main principle here, is how could we design this into our solution, whether that might be redecoration, it might be building a new cupboard. Oh, could I put a little hidden bit at the top of it to put some ducting in, or that sort of thing. So I'm going to say, I think broadly we've got an architectural audience, but I'd sort of say to you, actually, relatively early on, sort of REBA stage 2 concept design, maybe you should be thinking about the ventilation design and where you're going to hide some of these quite big services. So the rest of my presentation is a sort of little summary, as much as I can in 10 minutes, toolbox of some things you could think about, which just might help you think about the ventilation concept and build it into your design. I suggest you do an outline design yourself, design in a very loose term of just sort of, I want air to come in here, the duct's going to roughly run there, the fan's going to go here, and then you send it to a specialist and they can size the duct, size the unit, might make sure it's the right amount of air. But if you give them no guidelines, then they will, run ducts where you don't want them, and probably more ducts than you need potentially as well. So that's the ambition, is to help us on that. Okay, so here's some of the toolbox things. So my first one is sort of zoning. So a very, very basic system, and this goes for any system, not just MVHR, would have some supply air coming in somewhere, then it would go through some of the spaces, and then it would be extracted elsewhere. And you can make use of that. So in a house, there's only so many people. They're not going to be in every single room at every single time, at the same time, sorry. They will either be in the living room or they'll be in the bedroom. So if we think about when they're sort of soiling the air or making it dirty, they could be in any one of these spaces. So what we can do is we can sort of use the same air, put it in somewhere, take it through various spaces. At some point, it will meet the people who are in the building, and then it can be extracted elsewhere. And what that means is we don't have to run a duct and push air into every single space. So this is my house, and I've got a strategy where I put air into the living room, top corner here, and then I let it sort of waft through, and I'm opening, shutting doors, mixing it all up a lot, and eventually it finds its way through to the kitchen or up the stairs to the bathroom and a cupboard. And the spaces in between don't have anything in; they just get ventilated in between. Often in older properties, we've actually got an advantage because we don't have 4 ensuite bathrooms spread over the entire property in each corner to try and get to. It's often very sensibly stacked. Possibly in my case, I've got a rear return. Everything to do with servicing is in that rear return. That's where all the extract rooms are. And we quite commonly see that for particularly older buildings where there's a bit more, practically, it was the only place we could get a bathroom in because of the drainage or whatever. So that can be an advantage. And the last one on the zoning is that often the fan location is going to work better in somewhere where we're extracting from. That's because it's noisy. but also just in terms of running the ducts, that's quite a good strategy. So yeah, we're looking for somewhere in the extract zone to put the fan. Right. My second sort of toolbox thing is duct distribution. So there's two main types of duct that can be made of different materials, but two main ducts I'd consider in your designs. They've got different advantages. The bottom one is probably, I don't know, the easiest, but the ugliest. And this is semi-rigid plastic ducts. And they have you can bend them, but they have a smooth internal finish. And they're specifically designed for ventilation. And you can only bend them to a certain radius. And the strategy here is you run one or probably two or three ducts to each room terminal, so each room grill, and then they all come back like a big spider web to a central called a plenum where they all connect into, and then they connect into the ventilation unit. So these are the plenums. The advantage with that is the ducts themselves are quite small, maybe 90 mil radius. You need a lot of them, or an awful lot. They're quite tricky to run, but it's quite quick. And this is pretty much now used in new housing. It's the sort of method. So possible. The other one is to use a rigid ductwork. I prefer the sort of metal ones, but you can use a plastic duct as well. Ideally round, because with air, a bit like water, what we don't want is like very thin um, uh, routes for it to go through, because we're worried about the speed of the air. We want nice slow air movement. So for sort of efficiency of material and getting the slowest air movement we can, a circle is the best shape. But these will be bigger. So these might be up to, I don't know, 160 mil diameter, probably more likely 100, 120 mil diameter. And this one's a bit more like a tree diagram, like you've probably seen systems that are using this. And they can be mixed, so you can do a bit both, but typically you would do one or the other. Good. So big ducts is what we're aiming for, big or a lot of them to make one big duct. And so getting that into your design is hard. Typically, the horizontal runs are harder than the vertical ones. So if you can find a space where you can run horizontal ducts and then use vertical drops, that can be quite an efficient route. So that might be in some boxing in cupboards, like full height cupboards are quite a useful spot often, or the loft, or any roof space. Or it might be you've got a high ceiling in the ground floor and you can nick some space from the ceiling void. So those sorts of things are where we want to try and get horizontal as much as we can and then go vertical. And using the logic that already exists in the building. So a common one is chimneys. So here's an example of a chimney just being extended. So the fireplace actually offset already because there's another flue coming up next to it. So we could sort of center the chimney and we've put some boxing in to take the vertical duct in, and then it just looks like a chimney breast. So that's a vertical example. And then the horizontal example is hard to take photos of in a loft, but I've marked it up. So this is just doing all the horizontal runs in the loft. It's not ideal. It's outside the air tightness. There's some leakage issues. You want to make sure they're really sealed. It's a bit difficult to get back to. But as long as it's under the insulation, so within the thermal envelope, running ducts in the loft isn't such an issue. Not a great place for the unit itself because it's very, very dusty up there and pretty miserable, but not bad for ducts. So yeah, getting those around, that's really tough to do. The next thing we need to get that air to a room terminal, so somewhere where the air is either going to come in or out, and that could be ceiling mounted or it could be wall mounted. These I tend to favor keeping it really simple and using the horrible round ones, which maybe you don't like the look of. You can hide them, but try and use a round terminal because for the system setup, it makes it loads easier to measure and it's much more maintainable in the future. You can pull them off, rod the duct, clean it, and you can get things like filters for them, etc. So really, if you can, try and use the round ducts. As tempting as it might be to use a very neat slot diffuser, that will cause trouble later down the line. And if they're high up in a corner somewhere, you don't see that thing. Good. So opportunities is what we're looking for here. So we'd have to run ducts everywhere, but we're going to have somewhere where we need probably 150 mil for some attenuation, some little bends and things like that. Where could we hide it? So in this property, we've got some built-in cupboards where we've put something at high level coming out the wall, and we've got a kitchen with some space above it. That's quite a useful one, quite tight space above it, but some space. I also marked on the joists here because in this case we ended up using, the joists were going that way, which meant we could run one between the joists without having to drop the ceiling or anything like that. They're sort of looking for those opportunities. What was difficult was we've got a big structural beam coming through here, so we don't really want to be running ducts horizontally in this space. The main sort of spine wall comes down here, so we definitely can't go through there at all. And at the back of the property, the sort of existing wall here is really thick, so it's about 300 mil thick of lime and rubble, which means it's difficult to get through. So we only want to go through that once. So there's that sort of thought of like, okay, where are my constraints? What do I want to do? And the same, bringing air in at one end and taking it out the other. So here's an example, which I think is a potential solution in quite a few opportunities, new buildings as well. Sort of zoning the kitchen a little bit, particularly where it's open plan. Maybe this should have been brought forward a bit more to make it more of that sort of lower ceiling zone. And you get lots of space above it. And it's nice in a way because the kitchen unit layout is often long and you need a bit of length. You need some attenuators to reduce the noise, and you need the unit itself, and you need some access. So quite tricky. But that's an example. Again, in this case, the finishes were all there. It was all done on top. So the boxing in was all done on top. It wasn't ripping stuff, loads of dust. It was doing it retrofit. Good. So yeah, ducts and terminals, thinking about locations, thinking about your challenges. And then the last thing is this box. Where does it go? So this is a cupboard before the fans go in. There's sort of the two main types are in a box which has got all the ducts on top of it. So that needs a cupboard. You have to access it from the front. For those type, often the back of a cupboard is good rather than alongside stuff, because then you can pull everything out. And in my case, I've got a wheelie trolley, big sort of catering trolley, and we can just pull it out, which is the shelves. Or try, if you can, to have a dedicated cupboard, one with like doesn't really look like a cupboard. It looks like a wall with a very subtle opening. People forget about it, don't use it as storage. It's really tight, and that's probably better. Where you've got a cupboard which is like, well, it's clustered storage on the plan, but it happens to have a massive MVHR in the corner. That's trouble because people don't like it and maybe think about ripping it out. It gets damaged. Often the ductwork can be quite, it shouldn't be, but it can be quite vulnerable. And there's cabling controls, so the sort of mixing the two isn't great. Just trying to pull it out. Better might be, also this is just an example of that. It's a big unit. This is a new build. Trying to put it in its own cupboards. In this case, it does look like a cupboard. Admittedly, it's got architrave and everything, but it's quite nicely done in that it's right against an external wall. It's got some dropped ceiling, which sort of zones the kitchen. It's designed, it's thought about. And this is what I'm sort of talking about baking this in quite early, like designing it, using it as one of the constraints to inform your interior design as well as the practicalities. The other type of unit, which I think has probably got more legs and for retrofit, is the sort of ceiling mounted units. So these are much narrower and they tend to have two ducts at one end and two ducts at the other, in and out. From outside, sorry, and then two inside the building. And most of those can run either hung from a ceiling or can go vertical. So you can hide them in smaller spaces. And yeah, they also do lower flow rates. So for flats or smaller properties, they can work really well. Maintenance and access needs to be thought about. So you will need to access these to change filters. In the future, that might need to be replaced or at least a motor mended or something. Replaced, sorry. So you need to think about access, but that's sort of all possible. And I gave some rough, really crude. If you're thinking about it, don't look at just the unit. Remember, you've got some attenuators, so a good long length you need off the unit as well. Um, Good. So that's just some my thoughts. The main thing was, think about it early. Do feel free to do the design. There is no, it's a bit of an art form, this. There's specialists who will help you with the detail, but there's no reason you can't do an outline strategy for a ventilation design, and actually your project will benefit from it, no doubt. So you can do it. And yeah, be creative.
Great. Thank you very much, Will. That was very interesting, and it's very good to see applied to your house. Maybe we can start with a little bit of questions now. So one for you, Will, is are ventilation system noisy, or actually for both, because it's something we touched on.
Yeah. So yes, they can be. Is the is the answer. You've got a fan. If it's badly designed, and you've probably heard a rattly fan in bathroom when you go into the loo or something. A well-designed central system, you should not be able to hear. So if you can hear it, there's something that's gone wrong, or it's running at a very high flow rate. So at least these systems should be inaudible in homes. It's more than possible to do that. Um, so yeah, it's about the design. If you pinch something on the ceiling void and force letterbox ducts and can't have fit any attenuators in, it'll be noisy. So there's a sort of knock-on consequence of not allowing enough services space. So that should be sort of factored in. Yeah, I'm going to have to run and get a charger because I thought I
Okay.
would survive and I haven't, but
Yeah.
it's just there. Give me a second.
Simon, do you have anything to add, or should we move to next question?
Happy to jump to the next question. I'll buy Will some
Okay.
time as well.
Yeah.
Yeah.
Great. Then I'll do one that's probably more direct to you because it came during the your presentation. So it's quite technical. Dehumidifier can trap some particulate matter 2.5 and remove moisture and VOCs. In homes with adequate ventilation, can they provide additional improvement to air quality and mold risk reduction?
So this is dehumidifiers.
Yes.
Yeah, I mean, basically what you're starting to move into there is conditioning of the space, but beyond just ventilation. So using a dehumidifier to perhaps bring moisture loads down. It's an interesting one. You would get people that would argue that if you have adequate ventilation, you should be able to control moisture. Okay, is the first thing. But not all worlds are perfect. You may have homes that are very overoccupied or generating a lot of moisture where the ventilation system may struggle. Or you may have a building that struggles from a fabric perspective, an older building where even with good ventilation, the level of moisture is still causing issues with condensation. So properly designed, I've got no issue with dehumidification. It can certainly reduce the energy load of a property because dry air is cheaper to heat than moisture loaded air, certainly. But we also have to bear in mind unintended consequences. If if we focus too much on moisture, we start to assume that the absence of condensation means we have adequate ventilation. And if we're trying to solve a moisture problem, we have to remember that that's not the only problem. And if you remember my tree plot, actually moisture risk and mold isn't necessarily our largest risk. So what the question there is loaded with in a way is, well, some of these might have filters in them. So they're performing the air cleaning part, so they're adding filtration to the mix. Others may change the characteristics of the air through ionization or plasma or oxidation. There's a whole bunch of what we would call additive processes that effectively use air chemistry to have an impact on the air. We just have to be really careful in those environments. And I always put a big red flag the moment we move beyond anything other than just dehumidification and filtration. and we start physically changing the characteristics of the air, there's an enormous amount of unintended consequences from doing that that are very hard to measure, and potentially have downstream consequences on health and well-being. And most of the international organizations, the ASHRAEs, the REVAs, the SIBSes, and so on, will generally put a very big word of caution on what we call additive air cleaning. So cleaning that isn't subtractive, just removing pollutants through filtration or removing moisture through dehumidification, because the air chemistry is very complex. And as you saw with limonene, you can have a perfectly harmless pollutant or relatively harmless pollutant like effectively an essential oil. Pinene, limonenes are all part of that. That's what we call terpenes, but they come into contact with the wrong pollutant and they turn into other something else that is more harmful. So we do have to be very careful there.
Okay, thank
I
you.
think I'd just add, I suppose this is
Yeah.
probably thinking about the sort of room cooling, like the Dyson things, which filter air and blow air through them. Um, I'd add that they don't move an awful lot of air. You know, one of those is probably, I don't know what they're actually doing, but maybe 10 liters a second or something like that. Whereas a whole house system would be doing 50 liters a second easily, maybe, you know, across the whole whole home. So the order of magnitude of air you're moving with a proper ventilation system is a lot more than these sort of small units, which would make a lot of noise if they needed to move that amount of air.
I always just put a big word. I always just get people to really think about solutions that target one problem, because often risk keeps bad company. And we just have to be cognizant that we might be trying to deal with a damp and mold problem, for example, but usually damp and mold through lack of ventilation is going to mean exposure to other pollutants as well. We may deal with the damp and mold problem with dehumidification, but we may not be dealing with the particulate matter or the gases or something else in the process. And we think we've solved the problem because condensation starts to drop, but we may not have dealt with the thing that's actually causing the harm. So it's one of those things we have to be really careful of when we see products that can fix a problem, whether there's any unintended consequences of doing that.
Yeah. Maybe we can move on to heating and cooling. So there is a question about, can a ventilation system provide me with heating or cooling or both?
Good question. So yes, so short answer is yes, it can provide some heating and cooling, but certainly for existing buildings, it's not going to replace another system. So it'll be sort of supplementary, and the reason for that is sort of contrary to what I said. Although the quantity of air is a lot more than a single room system, actually the amount of air you're moving is relatively modest, and so it can't, and air has got a very low specific heat capacity, so it can't actually carry much heat or cool when compared to water or other fluids. So you to heat with air, you have to move a lot, which is why things like this thing up here, which is an air conditioning unit, blow a lot of air through and you can hear them. Um, so yeah, you can provide a little bit of supplementary heating and cooling through mechanical air systems. But the one for just the ventilation systems, they, you know, maybe it's not the most optimum. And you'd have to have a very low energy property, a small passive house, to be able to deliver all your heating and cooling with such a system.
But yes, in the short answer, there are some very good technologies out there that would provide both passive heating and cooling and active heating and cooling through combined heat pumping and exhaust airs and a whole range of things. So it is there's a lot of technology there. Again, to be the doom mongerer here, the general experience of the built environment has been, and I'm not saying it's always going to be the case, but has been that when we've tried to combine heating and ventilation in the same systems, we've generally done a very poor job of it. If you remember my stats of how badly we get ventilation wrong, even when we're just trying to move air, you imagine making that even more complex with heating and cooling as well. Um, the We don't have a great history of getting both right, and what we often find is in building failures where we've tried to combine it, that heating and comfort have overruled air quality and health, um, because people respond to discomfort faster than they respond to inadequate ventilation. So we find those systems generally tend to prioritize comfort over health. And even today, I'm consulting with a number of organizations that have invested in exhaust air heat pumps is a good example where the priority in the design has been for comfort and provision of effective heating, and it has had unintended consequences on ventilation performance.
And maybe
That's the
one last
challenge.
question. Sorry, we are only on the last 3 minutes, so I'm going to try to combine two together. So one is, how can we measure air quality, like for a client home, before and after, the ventilation system? And then as well, there is asking for a recommendation for a monitoring system, if you have any recommendation.
Shall I come in here, Will, on that one? I mean, anybody that looks at my office will see a whole array of various different air quality sensors measuring all sorts of different things. It is easier than it has ever been to monitor indoor air quality. We don't have to start very complex. We can start by monitoring temperature, humidity, and CO2 in properties, and combined, they will give us a very good picture of the thermal performance of that building and the ventilation performance of that building, because the main driver of CO2 in a property is us and our respiration, breathing. So measuring CO2 can be a good way or a good indicator of the effectiveness of ventilation in that space. Without us having to measure any specific pollutants at all, we can get a good idea of how well ventilated a place is. And that technology is very, very cheap these days. $100 or two will get you a relatively good CO2 temperature and humidity sensor, and you can start to learn about how a building performs. The interesting thing about air quality is that there's very limited value in a snapshot value of air quality in a property. Properties are very dynamic when it comes to air quality. So longitudinal measurements over months are ideal. And ideally, particularly depending on where you are in the world, in the heating or cooling cycle of that particular part of the world is very important as well. When we want to measure buildings when we're putting them under pressure thermally, where we start to close them off from the outside world, that's where it's going to impact air quality the most. So in our part of the world here, measuring through the heating season, so at least 2 or 3 months through the heating season, gives you a good picture of how that building is going to perform at its worst generally. That's what I would recommend. As far as products go, consumer grade products, there are great products by the likes of Aranet and Air Things and Imbiot and various other ones. If you do this regularly as an architect practice, spend a bit of time talking to the experts, because you may get technology that you can log into and look at dashboards and start to make decisions. And measuring air quality is a very good way of showing the efficacy of your intervention. So it's a great way of making the invisible visible for people and showing that the money that they've spent has actually had a good impact. So before and after is a really great way of showing what a good job you've done.
Yeah. I'd add there that, as Simon said, those three measures are probably enough. And if you could spend some more money and you had an option of spending it on measuring more things or more robust equipment that has remote access, I'd probably lean towards, robust equipment, maybe some scientific instrument sort of level, and certainly remote access is so useful for monitoring, because access to the properties is hard sometimes.
And can I just give one final shout out, please, to Radon, particularly when we're looking at existing buildings. Measuring radon will cost you 50 quid. It goes in for a couple of months before you start. When you're planning the retrofit and you're talking to clients, if they're in an area of high radon, look at the map and see if they are. If they are, buy them, get them to buy a radon sensor. You buy one, they're 50 quid. They stick them on the shelf for 3 months, send them off to the lab. We are undoubtedly at the moment fundamentally changing people's properties that already have high levels of radon, and we are making them worse and better. But the trouble is that we've got no idea often what the starting point was. And I am dealing with countless homes that have got high levels of radon post retrofit, And the problem is nobody in that design and supply chain has any idea whether they've made that problem better or worse. And that's a risk problem to those organizations, because people are quite rightly saying, I've spent a lot of money on this property. I'm sitting in a home that's got high levels of radon. I think you did this, and haven't got a leg to stand on. So be really careful. Whatever work you're doing, look to see if that home's in an area of high radon. If it is, recommend that they do a radon test. And if it comes back high, a remediation plan should form a central part of that retrofit plan. Because if it isn't, you're liable.
Okay, that was very informative. Yeah, thank you. It's past 2 o'clock now, so I think we need to say thank you to everybody that joined. Thank you, Simon, and thank you, Will. And yes, see you on the next ACAN. Thanks. Bye. Thanks, everyone.
Thanks. Bye.